Alright, you guys, here's the playroom. And now, isn't that a disaster? Look at the mess, man. This is my junk room. Boxes, radios, meters. Let's see. And I worked on this thing all night. This BroMikey's cap dump series of explanations. I had to fix that big dog because the meter burned out, and I need that to supply my cap dump, right? Look at this thing go. This thing is awesome now. Look at the meter, huh? Let me see that meter. Can you see that meter? Look at that baby jump. It's at 14 plus volts half the time, and well, let's see what it says right now. This meter's got to settle down. Well, I guess it ain't gonna settle down. This is a meter that you're not really supposed to use. It doesn't give any accurate reading down below. I used to look at batteries while they were charging and say, oh, it moved a point. This thing is moving a volt sometimes. And I got another meter here. Can you see that? There's my new meters with shunts. There's an input there, just a 5 or 6 amps. And then here's the other meter shunted, like I was telling you. Can't see it. Let me get over here. Can you see it now? Yeah, that's on the switch over there, and that's what the batteries get. I don't have very good connections there either, just hanging on wires, but it should do the job. And then here, you can see that ridiculous thing nailed up on this upside down component. This is nowhere near done. I'm just hanging this thing up so I can test it. I got my 3 FETs down there, and if you look under there, you'll see that bulb. You see that bulb at the top of the heatsink? That's your air conditioner bulb. It has gas in it, and the fan is running there. I don't know if that fan's blowing you guys away or not, but it'll shut off in a second. It don't run all the time. Putting my hand on it right now, it's barely warm. That's what you want. You don't want runaway thermal, right? On your FETs. But the fun part here is this. Look at that thing. Wanted to give you an update. And then there's that same old circuit just running along. Now, yeah, I could have controllers and fancy drivers, and I'm going to have all that. But to the guys out here who have a common 5.5 timer and they have a set of caps, it works. If you use the right FETs. The FET that you need is an IRFP, see it in there? It's an IRFP460. The 250s in my application, what I'm doing, does not work. They will burn up. Now, I've been running these for days and they haven't burned up. The 250s wouldn't last 2 minutes the way I'm using this. Now, how am I using it? Well, look at this dial here. I don't know if you can see it. I'm at 45 volts. See it there? Basically, I'm about at 45 volts on the input. But the cap bank is not 45 volts at this pulse rate. So yeah, like Matt said, a controller is in order, you know, in the long run. But right now I'm a beginner and I'm learning how to do these basic things. And get one of those $29 controllers or whatever and hang on there, and it's a done deal. You can program it and all that. That's a really marvel. A technological marvel how far advanced we are. But let's do our math longhand. Throw your calculator out the window. That's what I say. I'm from the old school. Throw your calculator and you pull out your slide rule. And that's, when I was going to school, we used a slide rule in math class, and we did all our math longhand, right on up to calculus. So yeah, calculators are nice, but let's not forget how to do it. And I know a lot of you guys know a whole lot more than me about it. I'm just having a lot of fun here. And look at that battery. You can't see it. It's in the basement, and it's 50 feet away, and it goes down a hole in the floor with PVC and those great big well, I think they're 70 or 80 amp cables, copper wire, one for each. Okay, but now when I move the wire here over to measure the amount of voltage in the cat bank for each pulse, you'll see an average. Now I could get my analog meter out here, but this gives you an idea. See, about 30 volts, 31 volts, and it goes down too far. Goes down sometimes to 16 volts, right? You see that average? 30 volts down to 15, 16 volts. It's a little too far down, but I'm getting some good pulses. Now let's say I wanted to be ridiculous and reach over here to the variac, right? And start turning it up, right? And I'm not supposed to do that. I might damage the battery. Or I'm being facetious, but you know, if you had a small battery, you might damage it. This thing is huge, and of course, even any battery you can damage, depending on how fast and how much power you're putting into it. So you want to be careful. But I'm talking in terms of my FETs now. I'm going to reach over here with one hand and show you my meter. Right? Try to hold it still with one hand, and I'm going to turn this up. Watch. See it go way up there? And of course or I can turn it way down. See, I can turn it way down, back down to where I was. 10 amp pulses. And I was up on the dial to 60. Now, I'm not going to stay there right now, but because those little FETs can't handle it for long, probably. But the point is, they can handle it. Especially if you're... Now let's go over here to the FETs and reach in there and feel them. Clip my finger off here with the fan. Steel fans are not fun. But it's not that hot. It's I can put my finger on it. It's fine. Oops. It's fine in there. It's probably maybe 90. I can get my thermal probe out, but I didn't done all that before. The point is, I'm back, and I wanted to show you the circuit's all hanging out everywhere, upside down and backwards. Only 1/4 of the FETs are installed, and they can handle it to some degree. I can't run my power levels up yet, and I have no intention of doing that until I get the other 3/4 of the FETs installed. But if you look down here at my new meter, you'll see I'm at like an average of 4 amps maybe, 1 to 8 amp surging there, and I'm at 45 volts. And then there's a voltage drop across this resistor, and I guess this is, you know, this is an RC charging of caps, right? So let me go across my resistor, and you guys that know how to do the math, tell me what this means. Let's see, I have to go across the resistor. I have to get a voltage drop. Let's see, that would be right here on the input and on the output of the resistor. I'm reading an average of sometimes, what is it? Sometimes 13 volts and sometimes 6 and 14 there, and 16 and 15. So an average it out, 16, 17 Is it going back down now? Averaging. These are little computerized things, average everything out. These meters, right? So 17 to 6 is 11 volt variance. Cut that in half. You got like, looks like about a 6 volt, well, what would that be? It'd be like a 10 volt drop across that resistor at the amp, and then an averaging out of the amps. So 4 and 10, so I'm losing about 40 watts out of this resistor, and I'm putting my hand on the top. I'm not running a fan right now, and it's mildly warm up there, and I should go down here and put the fan on, which I don't have all this stuff with supervisory circuits on that one yet. But you know, that's a waste there. 40 watts is a waste of power to charge. But in any charging where you have a huge heat sinks and any electronic high power handling, manipulating, you're going to have power losses, and you try to eliminate them. Now the smart move would be, like Matt said and a lot of the other guys would, to get rid of this battery charger here, which it's an option. It works with some losses, and go to the gen mode. Use the Bedini gen mode inverter style stuff, and of course I'm partial to using coils. So what is that? An average of, you just take the two numbers 6 and 17, add them together and cut it in half. 6 and 17, 23, so about 12 volts. 12 volts and an average of 11, we'll say 11 volts, and an average of 3 or 4 amps, maybe. I'm guessing. So that might be more. That might be more than 40 watts. I'm losing quite a bit there, and I'm running at 45 volts at 4, so I'm 160 watts, and my voltage drop considered across there, I don't know how much I'm losing. Maybe I'm losing half. Or wait, that would be like 4 times 10 would be 40. No, that would be 4 times 12 would be 48. So no, I'm losing 48, and I'm putting in like 180. So I'm realizing what, about 125 watts I'm getting into the battery, and I'm losing 50 watts because of that resistor. Because you got to slow down. You got to slow down the cap bank charging, or you'll blow the breaker on your house. All right, that's too hard on a. You got to charge up those caps. You know, you can't do it in nanoseconds every time, and just breaks everything electronically. And this video is for the beginners, okay? And all you guys are way ahead of me can understand the way I talk that I'm a beginner. So here it is, back working again. The point of these videos is to get one FET, and I'm angry every minute when I talk. I don't know if you guys sense this, but that is really aggravating me, that I had spent all this time to find out which FET to use, and very few people forward this FET. It's an IRFP460. You can beat the living daylights out of this FET, and it does what it's supposed to do. Don't use a 250 unless you wanna replace it and put freewheeling diodes across it and baby it and all this and that and change it so there's no ring in the circuit. You want ring if you can. I don't know if I know what I'm even talking about there, but somebody said, well, put a diode across there. I guess that's more for a coil. See, I don't know what I'm talking about there, but you know how they put diodes, fast fast response diodes where across the FET, like the FET has a built-in diode. Somebody please explain that if you get a chance to clarify the benefits of diodes that are fast acting in this setting. Would it help? But I just wanted to hurry back and let everybody know, look at my circuit, it's flashing. The 5.5 timer did not destroy my FET. The steering is not as bad as I thought. This was something that John Bedini put in a patent or had available for years for the beginners, right? And that's me. And everybody, a lot of other people are beginning, have to have somewhere to start. You see all these fancy supervisory circuits with never-ending digital controls on FETs, but we need to get our foot in the door on pulse technology. And since the 90s, John Bedini has been exploring it himself and sharing what he knows with others. So here it is. Here, again, I'm going to turn it up for you. I'm going to abuse that for just a minute. I'm going to show you where I can. Now I think I'm going up to about 60 when I go up there. Yeah, going up to like 60. And I'd let it sit there a while. And it gets warm. It gets pretty darn warm, you know, but it doesn't get that much warmer. I'm feeling it right now. I got my hand on it. It's barely warm. So, and my, you'll hear my machine start to groan down here. I don't know if you can hear it. I'm going to reach down here and turn it up for you. Can you hear it? Hear that humming? Maybe you can't hear it. It starts humming and groaning when it fills the caps. It takes a lot of power to fill those caps quickly. And I can run this thing up, so I'm pretty happy about it. You look at my amp, look at my, when I run this up, look where my amps go. See, it goes way up. Goes, and that's about as much as I dare go with this box, the way it's wired right now. And I just, you know, I'm doing testing to see what my waste is and what my voltage drop is. Again, let's change my battery around here right quick. Check the battery, right? And put it on, check the 12-volt battery, right? Before we end this video. And this is the cap bank, running at like 34 volts sometimes. I need to get this around here where you can see it, huh? There, can you see that better? Maybe a little better, huh? It's right on up there. The circuit's about ready to shut off, I think. Well, I got it up too high for the fan to shut off, but it will shut off. It's not that hot. And then here's that's what's going into the battery, and then here is the battery. I just switched the wires. 14.2, it's kicking its butt all around. That's a little bitty cap bank there. Really, it's only 90,000. I think it's 85 or 90,000 UF, but they're 250 volt caps in there. See them in there? Which lets me charge 2 batteries and keep an elevated amount of voltage in the bank, you know, versus the number of pulses per second, because that will drop what's going in there. Just as a for instance, I'm running at 45-50 volts right now. I'm running at 50 volts, but the cap bank is only maintaining, or what is it, an average of 36 volts, 35, 35.5, 36.2, and that's it. 36 volts or a little more. Yep, and it's going back down again. See the average? The computer is averaging. These meters have an averaging. So it's better to use analog meters. But once you get familiar with this, you can use a digital meter. You just gotta see the average. Alright. So I got like 20 or 15 volts more going into the cap bank, and it's discharging it when it's like 36 volts instead of 50. So I gotta have some sealing there. Now if I slow this down, watch me slow this down. Let me reach down here. See down here where my controls are? They're just hanging there. I just see it hang there, and everything just hanging on the bench to control the big power leads, right? Let me reach down here and change the timing. Ready? Okay, that's more and that's less. Now I'm going to go way down, just 1 pulse a second approx. Now look at the cap bank. Look where it is. I haven't moved anything. It's almost 50 volts because it takes some time to charge up fully from the power supply. Now look at my pulses over here on the wall. Can you see it? See that? They're way higher, but there's less of them. I get way higher surges, right? 15 amps. Well, that's more like who knows how many amps that is, but that is a big smash to a battery. And I need one because my battery is huge. So there you go. It's still working and it's going to stay working. I don't have time to babysit this every second, so I put that fan switch on there, and I don't want it running all the time if I don't need it, because in the day I just turn it down. Right now watch. I'm going to turn this down to where my pulses stop. I'm turning it down right now. See the pulses go down? Now I'm going to turn it down till there's nothing. Okay, that's my power supply. There's nothing coming in it now. Alright? It's off. It's not off, but it's off. And look at where my battery's setting. My battery is setting at 13.4, and it's never gone up to 15 or 16 volts that I can see. Of course, it's going to drop here. This is an alum battery, which are supposed to sit at like 11.7 or maybe 12 volt, 12.2. Sometimes I have batteries. This battery will probably set at 12.2 for days and days and days. That's where it has before. Every battery is a little bit different depending on how long it's conditioned and so many variables. This battery here is surprising me. I got to switch to the other side over here to that on that switch on the wall. We got to go to batteries on the right here pretty quick. But I'm really pleased with this FET and this timing circuit. And of course, you can improve it. We can improve it. But John Bedini has gotten me into the ground floor, so to speak, where I can. You guys can all make this circuit. Look at it. Let's see if we can see it down in there. See the light flashing? Yeah. You can see that circuit. Let me get a better angle on it. There ain't nothing to it. And it hadn't hurt it. I haven't damaged it like I thought maybe I had so many times when I was having so much trouble with those stupid 250s. Those 250 Mosfets are good for a 6 or a 12 volt battery. But when you want a high energy, high voltage surges, and the industry tells you, once you get up over 50 volts, you need to throw them out the window and get some FETs that can handle 500 volts. That 200 plus volts is not enough. See? Because you have, like Mario said, you have reflected. Can you see it? You can't see it without that, can you? You have reflected. There goes the fan. See, I told you. See, the fan's off now. See my ridiculous air conditioning I adjusted that. There's a hole in the front on these. See that hole right up above the dial? You can stick a watch screwdriver, stick it in there and turn it clockwise, and make it turn on at different, temperatures. You don't have to stay with what the air conditioners do. So see that hole right there in the front? Yeah, you can adjust that. And that's what I did, just a little bit. And that bulb sits on the heat sink there, and it turns on and off that fan. See that fan still running? And this thing is barely, not even, it's room temperature is what it is. Now we're going to go back on, and I'm going to leave you, because I got to get to work. But see my pulses going up? Up she goes. Come on up there. Yeah, I want a big one. Something like that would be nice. And that's like what, 45 volts here. Yeah, something like that. And see my amp surges. My amp surges are showing like 0 to 8 amps, so averaging in the time probably less than 4 amps. And there's a small fan on this too, and on the heat sink on the side, just barely, taking the heat off. And this is getting some pretty high surges, so I'm really excited about this. I'm just going to let it sit there and hang there, and the next move is to put all the FETs in to lower. That way we'll lower the I want to use the driver like this with all the FETs, and I'm wondering if this one large transistor right here would turn all 12 of them on without any problem. And I think it will, because it doesn't take much energy. But I really should have a push-pull driver system for this. So I might go to a push-pull to show everybody this next step from simplicity, from super simple to the next stage, because a push-pull, 2 transistors, an NPN and a PNP, working together is how they make driver circuits. And they don't have any driver chips that can handle 12, so I'm almost tempted to make my own driver chip, large scale, longhand, slide rule days, right? Tempted to make my own driver circuit that can handle all 12 MOSFETs. Okay, that's it for now. Now you know where I'm at. Coming up in understanding, learning, in the race, coming up from the back of the pack, so to speak. Okay, guys, thanks for all your input here on the energetic forum. This is Brother Mikey's Cap Dump Circuit signing off.